Today we are going to talk about transformations of the reciprocal function and work problems. So the reciprocal function is a special kind of rational function. It's the most baseline in that it's a fraction, but it's just 1 over x. So we are going to start by graphing this function. Let's say we make a table and we've got our inputs x and our outputs y, and then let's start with some really basic inputs. We'll go from -2 to +2. When we substitute -2 in there, we get 1 over -2, which is -1/2. And then 1 over -1 is -1. Now, when we do 1 over 0, we know if we try and divide anything by 0, that's no good. That's called undefined. And so something is going to happen at 0, but it's not going to be an output. So I'm going to put a question mark there for now. And then at 1, we're going to have an output of 1. And at 2, we're going to have an output of 1/2. So let's plot those points. -2, -1/2 is down here. -1, -1. 0, we don't know what's going on yet. We're going to find out. 1, 1. And 2, 1/2. So how do we connect these points to make a graph that's going to help us? Sometimes students like to just connect them and make a parallelogram, but that's not it. Instead, what we are going to do is connect these points like this. We are going to use 2 pieces, and these pieces are called branches. Now, notice how these branches are going toward the x-axis and the y-axis, but they're never actually touching them. The x and the y-axis are going to serve as guidelines. So we've got a guideline here that our branches are approaching but never touch. And then we have a guideline here that's doing the same thing. Now, pretend my lines are a little better and line up with the x-axis, but these guidelines are going to help us know where our branches go. Notice that our guidelines intersect at the point 0, 0. So there's a fancy math name for these guidelines, and that math name is asymptotes. And that's a crazy word, but it's just the math way to say guidelines, asymptotes. And our asymptotes intersect at 0, 0. We're also going to memorize 2 of our points, the easiest ones. We're going to memorize 1, 1 right here, and we're going to memorize -1, -1 right here. So if you can memorize these 3 points where your asymptotes intersect and then those key points, then you are going to be good to go when it comes to graphing these. So we're going to transform them now, and that means change them. And you'll notice here that we have A, H, and K, and those should look very familiar. You've seen them before. For example, you've seen them in transforming quadratics. We transform them with an A value out in front, x minus h squared plus k. It's the same a, the same h, and the same k. So what do they do to our parent graph, this graph right here? What are they going to do to it? Well, they're going to do the same things that they've always done. And that is our a value is going to let us stretch or compress our graph. And we're going to vertically stretch today, or always. It's a vertical, so it's either going to make it taller and skinnier or shorter than fatter. Our h value, if we see a minus h, we move to the right. And if we see a plus h, we move to the left. And then our k value, if we see plus k, we move up. And if we see minus k, we move down. So those are the rules. So let's look at some examples of our parent graph right here being transformed. So let's take a look. This first one right here. Remember, our parent graph is y equals 1 over x. So if we see a 1 right here, that matches the parent graph. So we don't have a stretch or compression. What we do have, though, is that it's moving to the right 3 units, and we also have that it's moving up 1 unit. So let's sketch this guy. Now, we'll always start with the asymptotes. Remember how our asymptotes by default intersected at 0, 0? Well, now we're moving this to the right 3 and up 1. So let's take that default intersection, move it to the right 3 and up 1. And now our guidelines are going to be here and here. Remember on our parent function how our default points were at 1, 1 and -1, -1? They still are, but now it's going to be based on our new asymptotes. So 1, 1 and -1, -1. Now we will draw our branches. So our branches will go through those points and they'll approach those guidelines while never actually crossing through them. And that is our transformation. It's our parent graph. If we scroll up, we can see our parent graph has been moved to the right 3 and up 1. So let's talk about domain. Remember, domain deals with the x values. So this function, these branches live everywhere except for one location. There's a break. And that break occurs at 3. That's where that branch is. There's nothing that lives there. So we are going to write our domain with a special symbol called a union. Because this is in 2 pieces, we need to write it as those separate pieces. So we go from -infinity up until 3. We don't actually touch 3, so we're going to have parentheses there. And then we're going to pick back up on the other side of the 3 and go to infinity. And then we're going to put a U between them. That's just the special math way of saying these together make the domain. Just like a union is like a marriage, you're together. These 2 intervals are together to make the whole domain. All right. So for whatever reason, my computer is making these look wonky, but they should be correct on your paper. So we've got y equals 2 over x plus 1. So let's go from there. This time, we do have a change in our a value. Instead of a 1, it's a 2. So we are transforming by stretching by a value of 2. And then this plus 1 right here also means we are moving to the left 1. We'll take care of the stretch in a second, but for now, let's start by moving our asymptotes. Normally, they intersect at 0, 0. Now we're moving them to the left 1. So our asymptotes, those guidelines, are going to intersect here and here. Whoop. I think my sleeve hit the computer screen. There we go. Okay. So now when it comes to stretch by 2, please, please, please remember that stretches are always vertical. They're always up and down. So normally we have points at 1, 1 and -1, -1. But now we're going to stretch them. Normally they have a height of 1, but now we're going to give them a height of 2. They're getting twice as tall. So our key points are going to be vertically 2 units away from our asymptotes, not just 1. So this thing got taller. Once you've got those key points in place, you don't have to worry about anything else. Just make your branches approach those asymptotes. So again, that stretch by 2 means our points normally were 1 unit tall. Now they are 2 units tall, either above or below the asymptote. So what's the domain? Well, remember, domain deals with the x-axis. And where does our break occur? Our break occurs right here at -1. So let's write our domain. We go from -infinity. We get up to -1, but we don't actually ever touch it. Remember, that's the point of that guideline. We pick back up on the other side, -1 to infinity, and then we put a union between them. All right, we're doing well. We've got 2 more to go. Again, I'm sorry my computer made this wonky, but again, it's correct on your paper. So this next one is y equals -1 over x plus 3. So first of all, we've got this plus 3 that's moving us up 3 units. We've got that under control. But here's something we didn't talk about yet. This negative right here. Now, a negative out in front, you know what it does. It reflects your graph. So at the very end, we're going to flip our graph upside down, and everything's going to be just fine. First, let's talk about our asymptotes. Normally it's at 0, 0, but this time we've got up 3. So our new intersection is going to be right here, up 3 units. And then we'll draw our guidelines through that intersection. Okay, so that's taken care of. Now to do our reflection. Normally our points are at 1, 1 and -1, -1, but now they're going to flip and they're going to go here and here instead. So our branches are normally in the first quadrant and the third quadrant. When we have a reflection, our branches live in the other 2 quadrants. Oops, there we go. Sorry, I keep hitting the eraser. There we go. So see how your parent function, the originals branches are in the first and the third. Now our branches are in the second and the fourth. All right, let's talk domain. Where does that break occur? I didn't even draw the asymptote. But that break occurs at 0. It happens at 0 along the x-axis. It happens here. So our domain is going to go from negative infinity to 0, union 0 to infinity. All right, last one. We got a lot going on. We're going to have y equals negative 3 over x minus 1 plus 2. So we've got a negative out in front. That means we're going to reflect. We've got a 3, which means we're going to stretch by 3. We've got right 1, and we've got up 2. All right, so let's start with dealing with the right 1, up 2. Right 1, up 2 means our asymptotes are going to intersect here. They tell us that's where our guidelines go. Cool. Now, we know we're going to stretch by 3, which means that our original points that are usually 1 away from the horizontal asymptote, or they're 1 unit tall, now they're going to get 3 units tall. So they're going to go here and here, because now they're each 1, 2, 3 away, 1, 2, 3 away, either above or below, but it changes the height, how tall they are. But we also see that we have to reflect. So this point right here is going to go live down here. And this point right here, we're going to reflect back up here. So now we have reflected our graph. And we're ready to draw our branches. Now I know it's kind of wonky to draw branches when it's this tall, but just do your best to go through the given point while approaching those asymptotes. So our domain is going to be broken up right here at positive 1. So negative infinity to 1, union 1 to infinity. So you can see that we've taken care of all the pieces. We see the reflection, it's flipped upside down. We see the stretch, it's 3 units tall instead of 1 unit tall. And then we see that it's moved to the right 1 and up 2, because normally our asymptotes intersect at 0, 0, but it's moved to the right 1 and up 2. So we've taken care of everything. So that was a crash course on graphing these. But let's talk about how they help us with actual problems. So these are called work problems, and they're called that because they talk about how long it takes people to work either independently or together. So here's the rule for work problems. It's 1 over time alone, so I'm going to say the time of the first person, plus 1 over the time of the second person equals 1 over their time together. So let's read this problem and we're going to apply this formula. So Jill and Colin are making cupcakes. Jill can bake and decorate a batch in 3 hours. Colin can do it in 4 hours. How much time will it take them if they work together? So do we know the time of the first person? Do we know how long it takes Jill to decorate her cupcakes? Yeah, we do. Do we know the time it takes Colin to decorate his cupcakes? Yes, we do. Do we know how long it takes them to bake together? No, that's what we want to find out. So this is going to be our unknown. So let's rewrite this formula. We know that Jill can do it in 3 hours. Colin can do it in 4 hours. How long does it take for them to work together? So we're looking for this x value. Now, the good news is we know how to solve problems like this. You've done it previously. You put the left side in Desmos with y equals, and then you put the right side in Desmos with y equals. So y equals 1/3 plus 1/4. Y equals 1 over x, and you will find where those points intersect. That location of intersection will tell you your final answer, that x value, how long does it take them to work together. So when you put those two equations into Desmos, you find that the intersection occurs at 1.714. So that tells you how long it'll take if they work together. So the answer, let me make some room. The answer is 1.714 hours. That's how long it takes them to work together. So let's try two more and then we'll be done. So John and Cindy are painting a fence. John's time is 6 hours. Cindy's time is 4.5 hours. How long will it take them if they work together? So the formula we're going to use is the same as before. 1 over John's time plus 1 over Cindy's time equals 1 over their time together. So we know John's time is 6 hours, so we know 1 over 6, plus we know Cindy's time is 4.5, so 1 over 4.5, equals 1 over, we don't know their time together, but we're going to find out, so we'll just put an X there as a placeholder, because it's what we want to know. The good news is we can use Desmos to help us. We put the left side in as y equals 1 over 6 plus 1 over 4.5. And then we put the right side in as y equals 1 over x. And we want to find the x value where these two functions intersect because we're looking for x. That's the unknown thing. And you will end up getting 2.571 hours. All right, last one. This one's a little bit different. We've got Erica and Rachel painting a room together. So we've got 1 over Erica's time plus 1 over Rachel's time equals 1 over their together time. Now we know Erica's time is 5 hours, so 1 over 5 plus, we don't know Rachel's time. How long would it take Rachel? We don't know. So we're going to leave Rachel's time unknown. But we know their time together. Together, they paint a room in 3 hours, so 1 over 3. So we'll do the same thing we did before. Don't let it scare you that the unknown is in a different position. We're still going to put the left side in Desmos, y equals 1 over 5 plus 1 over x, and the right side in Desmos, y equals 1 over 3, and find where those things intersect. And we end up getting 7.5 hours. And that makes sense that it would take Rachel longer to paint a room alone than it would for the two of them to do so together in 3 hours.